for the most part, the Lewis as a framework for drawing is a good model for us, and it's important to remember that Lewis diagrams are models. They're not real. They're a representation of reality that is convenient for us, and so, but it does come across limitations or complications. So that we're going to start to talk about. So the first thing I want to talk about is how do we deal with things like polyatomic ions, for example. So when we're dealing with ions, the first thing that we're always going to do is we are going to be doing things like, again, counting valence electrons. So a simple case would be something like ammonium, right? So NH4 plus. So remember, if it's a positively charged ion, it means we're missing electrons. So we want to keep track of things. So we'd say nitrogen normally has 5 valence electrons, and each hydrogen has 4. So that's 9 valence electrons. But we have a positive charge, so we remove electrons. We remove 1, right? So this is positive, so we have to remove 1 electron. Right? So this would be 9 minus 1, so we're going to have 8 electrons. Right? And so what we have to start to figure out is where do we do that from? And if we start by, all right, so we have each of our hydrogens. And then our nitrogen, 1, 2, 3, 4, 5, right? If we start connecting everything, we'll see nitrogen only has 3 unpaired electrons, but we could split up this pair. So if we linked everything together, right? We say, well, what if we do these and then this one and then maybe this one with this one here and then this one here. I mean, I'm just trying to sort of represent everything. So I could say, all right, so I have my nitrogen with 4 hydrogens and then 1 unpaired electron. But this wouldn't have a positive charge, right? Because this has, I've counted 9 electrons. So where do I remove that electron from? From the nitrogen. That one has to go. So N like this, and then the whole thing is positive. But how do I know that it's positive and where that positive charge actually is? So there are 2 different types of things that we have to count when we're dealing with Lewis diagrams. We have to count for what's called the octet rule, and we have to count formal charge. Now, most of the time, the octet rule is the make or break rule about whether or not we can evaluate a Lewis diagram. And formal charge is also important, but we have to look at it a little bit separately. So I want to start talking about the octet rule first. All right, so the octet rule. So these are rules for counting electrons to help us evaluate how good a Lewis diagram is. All right. And is it acceptable? Because just because I can draw stuff connected doesn't necessarily mean that that it's any good, right? Or that it represents reality. We have to be able to evaluate our model. And so the first part of the way we evaluate our model is by looking at how many electrons are surrounding an atom. And as a general rule, what we do is we count all the bonding electrons and all the non-bonding electrons. And they should almost always equal 8. We'll talk about exceptions later. So, what does that look like? So let's say we go back to something as simple as water. All right. So if I, why am I doing that? If I have water, so we've seen the Lewis diagram for water. It looks like this. Now, if we think about bonding from the point of atomic orbitals. So one of the things I haven't really said is that bonds occur by what's called the linear combination of atomic orbitals, which basically is that you have atomic orbitals, s orbitals, p orbitals, and they overlap with each other to form bonds. So you can imagine that each hydrogen atom, right, has a 1s orbital. And the oxygen in the middle has, and we're just going to look at the valence, it has its 2s and its 2p, right? So each hydrogen has 1 electron here, and then the oxygen has one, like that, right? So we see it's got 2 lone pairs and then 2 spots for bonding. And so what happens is this electron here will say go within here, get shared, and then this one will share into here. And you can see that for the elements that we deal with commonly, oxygen, nitrogen, carbon, for example, their valence is in n equals 2. And the orbitals that are available in n equals 2 are 2s and 2p. And well, and guess what? How many electrons do we have room for in 2s and 2p? 8. So the number of electrons surrounding those atoms cannot exceed 8. Now, there are exceptions on both sides. So there are atoms that can have incomplete octets, and then there's atoms that can have sort of expanded octets, or are a more complicated situation. But basically what we're going to see is that things like hydrogen, right? The valence of hydrogen is 1s. And how many electrons are there for room for in 1s? Well, there's only room for 2 electrons. So that means that when we count, say for hydrogen, how many electrons are around it, that's only 2. But oxygen should be 8. So what I'm going to do, so for hydrogen, I count both the electrons in the bond are shared. So I'm going to say 1, 2. So this one, its octet has, so we're going to, for each atom, we're going to do octet. All right, and this one has 2. That's good. This also has 2. And then for the oxygen, we 1, 2, 3, 4, and 2 for each bond. 5, 6, 7, 8. So 8. So this is good. The octet is this. So what that means is that in terms of the arrangement of electrons in this atom, that's acceptable, right? We're not breaking any rules because bonding comes from atoms which follow quantum mechanics. So everything kind of has to play nice together. When you're drawing a Lewis diagram for a compound, obviously you want to make sure you have the right number of electrons, but then you need to make sure that all of the atoms in there obey the octet rule within the exceptions that we're going to talk about. So the first one is hydrogen. Its octet should just be 2. Now, the next part of evaluating this is the formal charge. Excuse me. So for formal charge, it's basically a way for us to analyze the distribution of charge in a molecule and to see if it makes sense. And so here's the thing. water, the charge on water is zero, right? It's neutral. And so we want to make sure that each of the individual atoms, the charge on those atoms is also zero, and that overall the sum of the charges makes sense. So, for example, again, so the way we count for formal charges is a little bit different. Is we count, again, all the non-bonding electrons. But then we only count one electron from each bond. Okay? And then we have to do a comparison. And then we do, so first we count, then compare. So what we do is it'll make more sense when I give you an example. Compare to the number of electrons in a neutral atom. In the neutral atom. And this is important. It's the atom that we compare to. So like from the periodic table. So what does that mean? So if we go back to the case of water, right? So water looks like this. So if I'm going to count for formal charge, so let's say I take hydrogen. I count all the non-bonding electrons. In the case of hydrogen, there are none. So that's good. And then I count one electron from each bond. So that's one electron around the hydrogen. Now, if I look at the atom of hydrogen on the periodic table, it has one electron also, right? So I compare. So my hydrogen here has one electron in water, and from that I'm going to just subtract one electron on periodic. I'm just going to say on periodic table, not Tobel table. So that's 0, right? So the hydrogen has a formal charge of 0, and this one's the same. Now oxygen, I'm going to count. Remember, I'm going to say 1, 2, 3, 4. One electron from here, so that's 5, and one electron from here, that's 6. So oxygen has 6 electrons in water. And on the periodic table, oxygen is element number 6, and it has 6 electrons on the periodic table. So that is 0. And so it has a formal charge of 0. So that's good because water is neutral, and then the sum of all of these formal charges is 0. And that's good because I want the formal charges to add up, right? It's really important is that on the atoms, must equal it has to equal the charge on the molecule. So now what we're going to do is we're going to go backwards and look at the case of ammonium. So if I go back to ammonium, so ammonium was NH4 plus, and we said that the Lewis diagram from this was 1, 2, just like this. Okay. And so first, what are we going to do? We're going to count the octet for each element for the octet rule, right? So if we look at the hydrogens, each hydrogen has 2 electrons from the bond. That's it. That's the most it can have. So that's perfect. The nitrogen, again, has no lone pairs and 8 bonding electrons. So the octet rule here is good also. So that's good. So octet rule is okay. Now, what about the formal charge? So the whole thing is charged, but maybe we want to know, well, where is that positive charge in this molecule? Is it localized somewhere on one particular atom? And we can figure this out. So again, remember for formal charge, what we do is we count one electron from each bond, and then we count and we compare that to the number of electrons in the neutral atom from the periodic table. So hydrogen, each hydrogen for the formal charge has 1 electron. So the formal charge is 0 for each of these hydrogens. Let me just put those in pink. But let's look at the nitrogen. If we do our formal charge counting for the nitrogen, how many electrons are counted for the nitrogen? 4, right? 1 from each bond. 1, 2, 3, 4. So 4 electrons. And maybe the minus isn't the best way. But on the periodic table, how many electrons does a neutral nitrogen atom have? 5. So if I compare that to 5 electrons, right, it's missing 1. So it should have a charge of +1, right? So the formal charge of the nitrogen atom is +1. So that's where, when we talk about, yes, the whole thing is positively charged, but the positive charge in this case is actually on the nitrogen atom. It's the nitrogen atom that is positively charged. So we're going to look at a few other cases. What I want you to do right now is I want you to see, so hopefully you have a pen and paper or a pencil, something with you. It's really important that you try and do things like draw, right? Like that you have, when we're talking about Lewis diagrams and things like that, you're not just watching me, that you're trying either to copy me or you try and solve these by actually drawing. I want you to try and come up with Lewis diagrams for NO3-, the nitrate ion. All right, so take a minute and see if you can figure that out. So remember, the first thing you want to do is count the number of electrons and then adjust, like, a number of electrons that just based on the atoms, and then adjust for the charge. In this case, it's -1, so you have to add an electron. All right, so let's take a look at the nitrate ion. So nitrogen is 5 electrons. Oxygen is 6. 3 sixes is 18, and 5 is 23 plus 1. So that gives us 24 electrons. You'll notice, as a general rule, most species, atoms and ions have an even number of electrons. All right, and that's so that, again, that all the electrons can be paired. There are odd electron species. We will come across some of them. Now, one of the things that starts to happen is, how do I know how to arrange my atoms? Right? Like, it's really easy to when you have something very simple like water, when you've got a hydrogen and you're like, well, hydrogen can only make 1 bond, so that's got to go on the outside. But both oxygen and nitrogen can make more than 1 bond. So how do I know which atom goes where? Any ideas? That the least electronegative element should go in the middle. And that is a good rule of thumb. Obviously, if the least electronegative element is hydrogen, then that doesn't count. But otherwise, yeah, the least electronegative element generally goes in the middle. The other thing you can check is which one can make the most bonds. That often also goes in the middle. So we're actually going to take a little detour through common bonding patterns. This is really useful as a way to sort of help you build molecules quickly. So we're just going to look at, like, starting from, where are we going to start? From boron, right? So typically boron makes 3 bonds, no lone pairs. Boron turns out to be one of the exceptions. It can have what's called an incomplete octet, like hydrogen. Carbon, typically a neutral carbon atom has 4 bonds. Nitrogen, 3 bonds and 2 lone pairs. Oxygen, 2 lone pairs and 2 bonds. And then I'm going to use X because all the halogens are the same. 3 lone pairs and 1 bond. All right. So that's the start of this. Now, there's a few other rules of thumb that that you should follow when we're designing Lewis molecules and representing them as Lewis structures. Is that in general, all right, with the exception of carbon as a central atom, and we're going to spend a bunch of time on that in a little while, but in general, molecules tend to be compact structures rather than long chains of atoms, all right? And this has to do with bond strength. So I could think of, just off the top of my head, a few different ways that the atoms in a nitrate ion could potentially be arranged. For example, I could think of things like having, say, now obviously I haven't counted my electrons yet, but that seems like maybe something I could figure out, or something like that. Maybe, I don't really know. I'm just trying a bunch of different things. All right. And there's other possibilities too. But before we even go beyond this, there's a few things that we want to evaluate. All right. The first thing is geometries like this, where you have like a triangle, like a ring of atoms with only three members of the 3 atoms in the ring, or even 4. These don't work very well. We're going to talk about ideal bond angles a little later, and this puts a lot of strain on them. So you could make molecules with very small rings in them, but it's hard and they're very reactive, so they tend to not be ideal. Long chains like this, with the exception, again, of carbon, are usually uncommon. And the reason is that we end up, it's the types of bonds that form. All right. So whenever an atom bonds with itself, that's known as a homonuclear bond, right? Because it's 2 of the same nuclei. And in general, homonuclear bonds are very weak. All right. Heteronuclear bonds tend to be very weak, much stronger. Again, carbon is the exception. The OO bond here, for example, super, super weak. And so if there's a way for this molecule to arrange itself to form stronger bonds, it's going to. All right. Sometimes it's impossible, but it's something to keep in mind. So as a general rule, molecules form more compact structures. All right. So if we go back to this, so we have nitrate ion with 24 electrons. Now, one of the ways that we can start being a little more advanced in how we do this is, instead of writing out each atom with all its electrons and so on, is we can try and do some sketch of what the skeleton of this atom looks like of this molecule looks like how are the atoms connected to each other, at least with one bond, and then try and fill in all of our electrons. So we've decided here that the central atom is going to be nitrogen. and it's going to be surrounded by oxygen atoms. All right. Now, once we've done that, the next thing we're going to do is add in all of our valence electrons. So we have to add in 24, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. So I've got 23 electrons. I need one more. Where does it go? So it needs to go on an atom that has space for it. And the way we're going to evaluate that is by checking the octet rule of each atom. So if we look, for example, at the nitrogen, when we're checking for octet rule, it's 2 electrons from each bond and all the non-bonding. So 1, 2, 3, 4, 5, 6, 7, 8. So then nitrogen already has a complete octet. So there's no room for another electron there. But each of these oxygens has 1, 2, 3, 4, 5, 6, 7. 7. So each of them has room for one more electron. So I'm going to put that, I don't know, here. Right? So that works out. So I've got all of my electrons. And the problem now is that I don't have complete octets for these atoms. Right? I've got, so this nitrogen, the octet rule is okay. This oxygen also, 1, 2, 3, 4, 5, 6, 7, 8. That's okay. But these 2 oxygen atoms have incomplete octets. So what can I do? Well, the easiest thing is to say, well, I could share more electrons. Wouldn't that work? Right? If I share more electrons, I should be able to complete my octets, right? So for example, even though these are paired, I could do, say, that, right? And that's going to give me, so now I've made double bonds here. So I have this nitrogen here. Then I have this nitrogen here. Well, now, again, as soon as I make some kind of change, I need to reevaluate. Right? So if I check my octets for my oxygens, those are all good, right? 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. So we're doing okay. But what about nitrogen now? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Uh-oh. This one now has 10 electrons in its octet. That is not okay. All right. Remember the valence. This ties back to atomic orbitals. The valence of nitrogen is in n equals 2. So 2s and 2p. So what do we got? That's room for 8 electrons only. So no good. So what if instead we only share? So what if from here, instead of sharing both of those electrons, what if we just share, we split up this way? And that gives us, what is going on? That's going to give us then something that looks like this. Now, this is maybe a little bit better. We're not sure yet, because if we look at this, this one has an incomplete octet. And this one has too many electrons still. Right? This one has 9 electrons in its octet, and this one only has 7. I did make a mistake. That's why. Sorry, my bad. Nothing changed except me making a mistake. That's what it should look like. So here's the thing. One of the things that can happen, and that does happen in bonding, is that just because this electron, if you will, came from the nitrogen, doesn't mean that it stays there. All right? One of the things that you should kind of try and recognize or conceptualize is that when a reaction happens to form a molecule or a polyatomic ion, basically all the electrons just try and organize themselves in a way that has kind of the lowest potential energy generally. And so if that means that this electron here ends up somewhere else in our molecule, that's fine, right? So basically what we can imagine is that this electron here, again, unpaired electrons are highly reactive, and they tend not to stay that way. So if electrons have an opportunity to pair, they will. And even if it means that this happens, so that we end up with, no, not that. This. All right. So again, all we're doing right now still is trying to evaluate this at the level of the octet rule. So now we're going to go and check the octet. All right. I'm going to label the oxygens A, B, and C so we can differentiate them. So we'll start with the nitrogen. So the nitrogen has 1, 2, 3, 4, 5, 6, 7, 8. So the nitrogen has 8. That's beautiful. Patrick, go ahead.
Yeah, just with the one you labeled as B, or A actually, would it make a difference if you had put the 2 electrons closer to each other? So instead of being on either side of oxygen, being adjacent to each
It's
other.
irrelevant. So Lewis diagrams have no geometry. All right?
Oh, okay.
It doesn't matter where I put them.
Okay.
There are, when we start drawing in 3 dimensions, yeah, it matters. But now it doesn't. All right? So oxygen A. Actually, what we're going to do, there we go, octet, and then we're going to do formal charge afterwards. Okay. So oxygen A, 1, 2, 3, 4, 5, 6, 7, 8, also 8, so that's good. Oxygen B, 1, 2, 3, 4, 5, 6, 7, 8. So that's good. And oxygen C, 1, 2, 3, 4, 5, 6, 7, 8. So that's also good. So we've managed to get to the first step of making this reasonable. Now I want to look at formal charge. So I'm just going to write FC. All right. So oxygen, let's go with the nitrogen. So what's the formal charge on the nitrogen in this molecule or this ion? I count 1 electron from each bond. So 1, 2, 3, 4. A neutral nitrogen atom has 5, so I'm missing 1. So the formal charge here is +1. Oxygen A, the formal charge is... No, all right. Well, the formal charge here is 0, right? 1, 2, 3, 4, 5, 6, right? And so 6 electrons and 6, so here it's 0. That's good. How about oxygen B? What's the formal charge on oxygen B? Yeah, that's right, Skylar, -1, because 1, 2, 3, 4, 5, 6, 7. Neutral oxygen has 6. That's 1 extra electron. That's -1. And then this oxygen has also the same thing. 1, 2, 3, 4, 5, 6, 7. So that's also -1. And so I could write that like this: plus -1. Oh, no, that one's 0. Sorry. -1 and -1. Now, is this a problem? Well, the answer actually is it's no. It's not a problem because the sum of the formal charges is -1, right? The sum is -1. And guess what? Nitrate is -1. So it's okay. Okay, so the way formal charges work is it's a slightly different counting, right? So octet rule, we count all the electrons. So all the non-bonding electrons and both electrons in a bond. For formal charge, we count all the non-bonding electrons, but we only count 1 electron from each bond. So that's why for, say, this oxygen here, that's 4 non-bonding electrons, so that's 4, but then only 1 from each electron, so that's 4, 5, 6. That's it. That's how we would count for formal charge. Now, when it comes to formal charge, when it comes to formal charge, there's a few things that we want to try and evaluate. So the basic rule is that the sum of the formal charges has to equal the overall charge in the atom or the ion. But there are some other rules that we want to try and evaluate in there, because as we get to more and more complex molecules or polyatomic ions, there are often variations that could come up, and we want to be able to try and decide, well, which one is better, which one is more likely to be the real molecule. And the other things that we need to evaluate are, aside from making sure that the formal charges add up, the other thing that we need to do is we want to make sure that any negative formal charges are on the most electronegative atoms in our molecule. All right, so in the case of nitrate, oxygen is more electronegative than nitrogen, so it makes sense for the oxygen atoms to carry any negative charges. And the other thing is that in general, we want to have the fewest charged atoms possible with the lowest magnitude of formal charge possible when that works out. Okay, so that's how that kind of works, right? So when we're evaluating the formal charge, let's see if I have another example to try and understand that a little bit. Let's take the cyanate ion, OCN minus. Yeah, so OCN minus has 6, 10, 15, 16 electrons. All right. Foolish me. All right, let's take a step back here. So we have OCN minus, the isocyanate ion. So I'm telling you, sorry, right now, carbon is in the middle. So we have oxygen, carbon, nitrogen, and then we start adding electrons. So 1, 2, just completing our octets. Not completing just adding in what we think are the missing electrons. So this gives me 15 electrons, right? This is just with the normal atoms. And then I have 16, and so that extra one is going to go in with the oxygen, because oxygen is the most electronegative element in the molecule. So that puts me there. And now what I'm going to do is I'm going to try and pair stuff up. Right? So the carbon has 2 unpaired electrons. The nitrogen has 2 unpaired electrons. So here we go like this. And this gives me this. And if I evaluate this Lewis diagram, I could have, let's see, formal. So I think the octet rule is satisfied for all of these atoms. And the formal charge, so the nitrogen, 1, 2, let's count for octet rule. 1, 2, 3, 4, 5, 6, 7, 8. So the octet rule is satisfied. How about formal charge? 1, 2, 3, 4, 5. So that's good. So the formal charge on this nitrogen is 0. Carbon, for octet rule, 2, 4, 6, 8. So that's good. And then the formal charge, 1, 2, 3, 4. Neutral carbon atom also has 4. So that's perfect. That's 0. For the oxygen, 1, 2, 3, 4, 5, 6, 7, 8. So octet rule is satisfied. For the formal charge, 1, 2, 3, 4, 5, 6, and 1, 7, minus 1. So that's good. But I could imagine a Lewis diagram for this molecule that looks like this. Right? And if I come up with this one, I'm like, well, let's evaluate Lewis octet and formal charge. So 1, 2, 3, 4, 5, 6, 7, 8. Octet rule is satisfied. Formal charge, 1, 2, 3, 4, 5, 6. Neutral nitrogen should have 5. So the formal charge here is minus 1. Carbon, octet rule, 2, 4, 6, 8. That's great. Formal charge, 1, 2, 3, 4. Also good. Formal charge of 0. How about this oxygen? For the octet rule, 1, 2, 3, 4, 5, 6, 7, 8. That's satisfied. And for formal charge, 1, 2, 3, 4, 5, 6, 0. So both of these Lewis diagrams actually satisfy the octet rule. They satisfy the formal charge. But when I need to evaluate which one is going to be closer to what the actual isocyanate ion looks like, I'm gonna choose this one. So this would be the more stable one, because the negative is on the most electronegative element. All right. So when I'm making a decision, now we're going to talk about how this gets more complicated again in a minute. And you have to remember that we are modeling very complex systems. Atoms are complex systems, and we're modeling them on paper. Right? We're modeling a probabilistic entity, right? Remember, it's quantum on paper. So we do the best we can, and we're going to start coming up against some problems. So we will come back to this one. Any questions before I move on? If this is the molecule ozone, like from the ozone layer, O3, and I can draw a Lewis diagram for it, and it looks like this. All right, octet rule, formal charge, all work out. Now, I pointed out before, Lewis diagrams don't have any geometry, right? So if I take this whole thing and I flip it upside down, or I put a mirror plane here, these two things, they could be mirror images of each other, right? And that would be fine because molecules move in space. So that's okay. But one of the things that is tricky about this, and this is something that causes, come on, there we go, a lot of headaches for people. And so I'm hoping we can find a way to try and avoid this. We'll see. I don't know if it'll work. So these, we could see these as mirror images of each other. But what if I did something like labeling these atoms? Right? What if I labeled these oxygens A, B, and C, and I did also this, oxygens A, B, and C. Now, I'm using A, B, and C, but we can actually do similar things in real life by using isotope labeling. So, for example, you could prepare in a lab ozone where only one of the oxygen atoms is, say, oxygen 18. Right? And you could decide, I want it to be the middle one. I want it to be one of the terminal ones. I could make it where both of the terminal ones are oxygen 18. It's pretty sophisticated what can be done. So it's kind of a more sophisticated version of labeling them as A, B, and C. So we can tell them apart. Now, when that happens, these two Lewis diagrams aren't identical anymore. They're not mirror images of each other, right? Once I've labeled these oxygens. But if I had to evaluate these Lewis diagrams, am I able to say that one, let's call this one, this is number 1, and this is number 2. Am I able to say that one is better according to the rules of Lewis diagrams than the other? Well, the answer is no, I can't. Both of these are equivalent. Right? Now, the other thing is, that's not a Z, that's a 2, is that there are ways for us to measure bond lengths in atoms, like actual experiments we can do. One of the classic techniques is something called X-ray diffraction. So basically what you do is you grow crystals of a compound, and you could do this even with ozone by freezing it, and you shoot X-rays at it, and the X-rays scatter, and then based on the scattering pattern, you can reconstruct how far apart different atoms are from each other. And so you can measure bond lengths. Now, if this Lewis diagram is accurate, I would expect that in an ozone molecule, I would have one double bond and one single bond. And that there should be probably then an even distribution of ones that look like this and ones that look like this. But that's not what happens. When we measure bond lengths in ozone, we find that both oxygen-oxygen bonds are the same length, and they're actually right in between. In terms of the bond lengths, they fall right in the middle between a single bond and a double bond. All right? So basically what happens is the real molecule exists as a hybrid, or almost an average. Kind of like an average. So the real molecule, I have to represent kind of like this. And each of these is a 1.5 bond. That's just the way it is. So when I have multiple Lewis structures for the same atom, for the same molecule, or for the same polyatomic ion that are equivalent or very nearly equivalent to each other, the real molecule actually exists as what's called a resonance hybrid. Up here, these would then be called the resonance contributors, and this is the resonance hybrid. Now, a lot of people misunderstand how resonance works. Because of how we draw it, how we conceptualize it, it's easy to think that what actually happens is the molecule is rapidly switching back and forth between these two forms. But that's not what happens, right? The molecule actually exists in this form, right? As a one, what we would decide is a 1.5 bond. There's no rule that says bonds have to be whole number units of electron sharing. That's an arbitrary decision that we've made to try and simplify things. It's often the case, but it's not always the case. All right, so there are lots of possible situations where resonance comes up. So, for example, if we go back to other examples that we saw, right? For example, the nitrate ion. Right, so we had a Lewis diagram for the nitrate ion that looked like this. Plus, minus, minus. Right? Now, if I do the same thing and label these oxygen atoms, I can see at least two other ways of drawing equivalent Lewis diagrams. Right? I could draw like this. And I could also draw it like this. And then I relate these to each other with a very specific type of arrow. I'm warning you guys now. Chemists are very particular about arrows. Okay? So this type of arrow, that's how you indicate that these structures are resonance contributors. All right? It's not the same as, right? Remember this? That's an equilibrium arrow, right? This is equilibrium. This is resonance. They're not the same. And so my hybrid, right? Hold on. So back to where we were. So the actual molecule is going to look like an average of these three because all of these three are the same as each other in terms of evaluating them as Lewis diagrams. And so they're all going to probably look like something like that. And the whole thing is going to be -1. Now my question is, what types of bonds are these now? One and a third. So when we're talking about whether it's a single bond or a double bond or a triple bond, we refer to that as the bond order. All right. And the way we calculate that is we say, well, what's the number of bonds that there are? And we divide that by how many? I'm just going to call it the number of positions, I guess. So in this case, in nitrate, we've got 4 bonds shared over 3 positions, right? So 4 on 3, so that's 1 1/3. So each of these bonds is a 1 1/3 bond, and they're all equivalent. And in real life, when we look at the structure of a nitrate ion, that's what we see. All of the NO bonds are the same length, and they are shorter than a single bond, longer than a double bond, right at the 1 1/3 sort of distance. Now, the last point I want to make for today with the resonance is that it doesn't only occur when there's equal sharing. Resonance is very, very common. And if we go back, for example, to the cyanate ion that we saw previously, right? So for the cyanate ion, we came up with 2 possible Lewis diagrams. Resonance is present in this case where we have multiple Lewis diagrams for the same molecule or polyatomic ion, and either they are equivalent, following our rules for evaluating Lewis structures, right? Formal charge, octet rule. They're equivalent to each other, so the real molecule is somewhere in between. All right. And when all of the contributing structures are equivalent to each other, then the resonance hybrid is an average. It's just a straight up average of them. There are situations where the Lewis structures that I can draw aren't equivalent to each other, but they're close. The truth of the matter is, a negative charge on a nitrogen is not a terrible thing, because it's I put my own hand up. A negative charge on a nitrogen isn't a terrible thing because a nitrogen's pretty electronegative. But this one here is still better. So what that means is that the real molecule or the real ion of isocyanate is still going to exist as some hybrid between these 2 structures, but I can't be as sure about, say, what the bond order is going to be. I don't really know. It's going to still be in between. Like if I had to bet, I would say this OC bond in the real isocyanate is going to be a little bit shorter than a single bond, and this CN bond is going to be a little bit longer than a triple bond, right? It's not an exact average between the 2 because the resonance structures aren't exactly equivalent, but it's still there.